Hey guys, I'm Samuel Pakalapati from Intel, and I'm going to talk about our prefetching framework, a bouquet of instruction pointers, also known as IPCP. Our hardware prefetching framework is based on control flow, as in the instruction pointer is used to identify access patterns and use this information for prefetching. Bouquet is hence a collection of tiny component prefetchers, all of which use the IP as a reference for prefetching. The training is done at the L1 level, and this knowledge is used to perform prefetching at both the L1 and the L2 levels. Our prefetching framework is extremely lightweight. The combined storage requirement at both the L1 and L2 levels is only 895 bytes. The performance improvement is 45% over a baseline with no prefetching for memory-intensive Spec 2017 benchmarks. Before getting into the topic, let's start with a bit of background. What is the memory wall? The memory wall problem refers to the increasing disparity between processor and DRAM speeds. The CPUs are usually way faster than DRAM memories. This means that if a cache line is not found in the entire cache hierarchy, it has to be brought in from the DRAM. The processor has to wait for a lot of cycles for the cache line to be filled into the cache, and this degrades performance. Hence, minimizing these costly DRAM accesses is crucial to improve performance, and prefetching is one way to do that. Broadly speaking, prefetchers can be classified into spatial and non-spatial ones. To understand them better, consider the following access pattern, which occurs in the temporal order. Three different regions A, B, and C are accessed. A spatial prefetcher trains and prefetches based on the accesses observed within a fixed region. In our case, access A acts as a trigger for the prefetching of A plus 2, A plus 3, and A plus 7. A non-spatial prefetcher can train on and prefetch cache lines from various regions. In the example, the prefetcher has identified the trigger A and goes on to prefetch cache lines in regions B and C as well. Our focus in IPCP is on spatial prefetching. Using a perfect prefetcher, one can prefetch all the required cache lines into the L1 and achieve 100% L1 hit rate. This would resolve the memory wall problem too. But most of the state-of-the-art prefetchers are situated at the L2 level. Let us look at the opportunity that lies in L1 prefetching. A perfect L1D prefetcher can achieve performance gains of up to 130%, while most of the state-of-the-art prefetchers achieve a maximum performance improvement of around 40%. This shows that there is a lot of room for improvement which can be exploited through L1 prefetching. We tested out various prefetchers at different cache levels to observe the difference in performance. In all these cases, prefetching and filling at the L1 was found to be more beneficial than prefetching at the L2 or filling till the L2. Why is the L1D the best place for prefetching? The prefetcher has access to an unfiltered memory access pattern. The pattern observed at the L2 is not only filtered by L1 hits, but in the presence of an L1 prefetcher is also jumbled with L1 demand and prefetch requests. The L1 prefetcher also has the added benefit of choosing where to place the prefetched cache lines. They can be placed in either the L1, L2, or the L3 levels. An ideal L1 prefetcher can also make the L2 cache redundant for certain applications. Given all the benefits of L1 prefetching, there are certain challenges to be addressed. Firstly, the lookup latency at the L1 cache and consequently that of the L1 prefetcher has to be very small, in the order of a few cycles, or else the prefetch requests would be issued too late to be of any use. This means that the L1 prefetcher has to be extremely tiny. Secondly, the L1 is already bandwidth starved and heavily ported. The prefetcher probes the L1 cache to find out whether the cache line is already present at L1. In order to save bandwidth, the number of such lookups has to be minimal. This means that the prefetches have to be highly accurate, timely, and less in number in order to make the most use out of this tiny bandwidth. Thirdly, the MSHR and the prefetch queue at the L1 have limited entries. If the L1 prefetcher prefetches too aggressively for a single IP, the consequent IPs might not find enough entries to issue prefetches or demand requests. Most of the current state-of-the-art prefetchers are highly tuned for specific memory access patterns. They demand a lot of space to cover a specific access pattern. Thus, when an additional pattern needs to be covered, the prefetcher size increases drastically. This in turn increases the lookup latency and makes it unsuitable for the implementation at L1. For example, prefetchers like SMS and Bingo consume around 100 KB of storage space. IPCP is a bouquet of 4 spatial classes. Each class is distinguished by the way it interacts with the control flow and data flow. The constant stride class uses the IP to identify strides, which are then used to prefetch the next access. Therefore, this is solely control flow driven. The complex stride class associates stride access patterns instead of just a single stride with the corresponding IP to make a prediction. Hence, this couples control flow with data flow. In the case of the global stream class, the IPs are used to predict if a region is going to exhibit stream-like behavior. In this case, the control flow is used to predict data flow behavior. The next line prefetcher depends on misses per kilocycles to decide whether or not to prefetch. IPCP is also highly modular. Temporal prefetchers like ISB and linked data structure prefetchers, which use the IP, can be seamlessly integrated into the framework, since they can simply be considered as yet another class. The constant stride class aims to simply capture the strides associated with an IP. When a stride is seen for a sufficient number of times, it is used to prefetch the next access. In this example, we see a constant stride of 2. The confidence counter is incremented every time the same stride is seen and decremented otherwise. The stride and the confidence are stored in the IP table. The drawback of this class is that it can only identify strides and not stride patterns, which brings us to the next class. Consider the following access pattern. It produces a stride pattern of +1, +2, and +3, and so on. The complex stride class is able to identify this pattern and prefetch the next access. Let's see how this works. We stored the stride patterns as a signature that predicts the future strides that will follow this pattern. This signature, which is stored in the IP table, is used to index to the complex stride prediction table to get the new stride. This stride is then hashed with the old signature by shifting the signature and XORing it with the latest stride to get the new signature. And this process continues till the prefetch degree is reached. Now, why would we need the CS class when the CPLX class can identify the constant strides too? This is because when a rogue stride is observed in the pattern, the CPLX class constructs an entirely new access pattern, since it incorporates this stride into the signature. During this time, it would be unable to issue any prefetches. The CS class, on the other hand, is tolerant towards such strides, and prefetching would continue without interruption. Let's now move on to the global stream class. Take the following region for example. 3 different IPs are accessing it. IPX acts as a trigger for the global stream in the region. In this case, it is better to prefetch the global stream instead of the strides observed by the IP, since it follows program order and hence results in better timeliness. It also exploits spatial locality, since the consecutive cache lines are potentially stored in the same DRAM row buffer, which results in increased row buffer hits. In order to understand how IPCP learns global stream, let's take a simple example. In the next slide, I will talk about the actual implementation. The accesses made by the IPs X, Y, and Z are all part of the same stream. These accesses are captured in a global history buffer in the temporal order. When an IP, say IPX, accesses a cache line, the GHB is looked up to see how many of the previous accesses would have been part of the stream initiated by IPX. If the majority of the accesses, say 3/4 of the entries in the buffer, are part of the global stream initiated by IPX, it would be safe to say that IPX is part of a global stream, and this stream would potentially cover accesses made by other IPs in the stream as well. We use a table called region stream table, where each entry stores a bit vector corresponding to the cache lines in a region. With each cache line being accessed in the region, the dense counter is incremented. When a sufficient number of cache lines are accessed in a region, it is marked as a dense region. All the IPs accessing it are labeled stream IPs. When a stream IP accesses a new region, the region is tentatively assumed to be a stream region. This removes the need for a region to be trained from the scratch for prefetching to happen. It has to be noted that a region is tentatively proclaimed as stream only when the region accessed before was trained and confirmed to be a stream region. This reduces the possibility of regions being spuriously classified as stream. The next line prefetcher simply prefetches the next cache line in space. However, we notice that this is detrimental to performance in some cases, especially when there are irregular accesses. Hence, we only prefetch the next line when the L1 misses per kilocycles, or MPKC, is lower than a certain threshold. When this is high, it means that there are too many misses being processed, and an inaccurate NL prefetcher can only make things worse by getting in the way of high priority demand requests. We've seen all the components of IPCP at L1. So how does it work? Upon an L1 access, the IP table and the region stream table are accessed simultaneously. Region stream training happens along with prefetching. If the region is dense enough, the stream valid bit in the IP table is updated. Meanwhile, at the IP table, if the IP belongs to the global stream class, stream prefetching is carried out. In the same cycle, the complex stride prediction table is looked up to get the CPLX stride. If the IP does not belong to the GS class, the confidence level of the CS class is checked out. If this confidence is high enough, prefetching is done using the constant stride. If not, CPLX prefetching happens, given that the CPLX stride confidence is high enough. If it isn't, a simple next line prefetcher is used. Hence, the priority of the classes is GS, CS, CPLX, and then NL. The default prefetch degree at L1 is 6 for GS class and 3 for the CS and CPLX classes. The degree is controlled through a throttling mechanism. Let's see how it is implemented. We use a per class throttling mechanism to control the prefetch degrees of the various classes at the L1D. Each cache line at the L1 contains 2 bits to indicate the class of the issued prefetch. 2 counters are assigned to every class, one to count the number of issued prefetches and the other for the number of useful prefetches. When a prefetch is issued or a prefetched line is accessed, these counters are updated. These counters are used to calculate the accuracy in every epoch, and this value is used to throttle the prefetch degree. IPCP at the L2 level is very simple and is constructed entirely using the metadata received from the L1 level. The reason IPCP cannot train at the L2 is that the access pattern at this level is jumbled from the prefetch and demand requests from L1, in addition to the L1 already acting as a filter for demand requests. The metadata contains the class type and the stride values. The IP table at this level is trained using the metadata, which piggybacks onto L1 prefetch requests and prefetches on both demand and prefetch requests from L1. We use an extended ChampSim simulator, which uses virtual addresses at the L1 to model IPCP. The memory model uses 32 KB instruction cache, 48 KB L1 data cache, 512 KB L2, and 2 MB per core shared LLC. The 48 KB L1 data cache is the same size as is used in Intel Ice Lake processors. We simulate Spec 2017 and Cloud Suite benchmarks. IPCP is compared with several state-of-the-art prefetchers. Let's look at the performance of various prefetchers at the L1 for memory-intensive spec workloads. IPCP implemented only at the L1 outperforms all the other prefetchers with a storage requirement of less than 1 KB. Only Bingo, with a size of 119 KB, is able to give a better performance than IPCP at L1. This makes a strong case for IPCP as an L1 prefetcher. This is how the performance looks like when IPCP is used at both L1 and L2. We compare IPCP with three competitive multi-level prefetching combinations. Benchmarks like GCC and B-Waves are very amenable to prefetching, whereas a few MCF phases, Perlbench, OmnetPP, and XZ confer negligible gains through prefetching. With some of the other prefetchers, these benchmarks even show performance degradation, which is avoided in IPCP through the use of accuracy counters. On average, IPCP provides 45% performance improvement over a baseline with no prefetching on memory-intensive traces and 22% improvement on the entire Spec CPU 2017 suite. Adding additional prefetchers at the L2 along with IPCP at the L1 provides negligible utility. The benchmarks where IPCP gives low performance improvement are the ones which report low coverage. This is due to a lot of irregular accesses made in these benchmarks, which cannot be captured by the component prefetchers in IPCP. The coverage is 60% at the L1, 70% at the L2, and 80% at the LLC. Let's look at how each class contributes to the overall coverage. CS class contribution to the prefetch coverage is fairly consistent across the benchmarks. The next most useful class being the GS class. CPLX class is helpful in benchmarks like MCF, Cactus, and Photonic. The use of next line prefetcher in some of the benchmarks indicates the presence of irregular accesses. Together, GS and CS classes contribute to 80% of the overall prefetch coverage of IPCP. Let's understand the utility of each class and combination of classes. A combination of classes is better than any class used as a standalone prefetcher. CPLX and CS class together is better than CPLX used alone, which shows that there are indeed certain accesses which are better covered by CS, even though they might be a subset of those covered by CPLX. The combined framework at both the L1 and L2 gives the maximum performance improvement of 45%. We also tested out the priority of the classes, and the order GS, CS, CPLX is the best one. This can be attributed to the timeliness and locality exploitation of the GS class and the resistance of CS class towards spurious strides. In the multi-core scenario, it is difficult to get performance improvements due to limited DRAM bandwidth. The accuracy throttling feature enables IPCP to reduce performance degradation when heterogeneous mixes are used. On average, IPCP provides performance improvement of 23.4%, while the next best, Bingo and MLOP, provide 20.9% and 20% respectively. The IP classification is done based on control and data flows. The result is a bouquet of IP prefetchers with a hierarchical priority model. It uses metadata for coordination among the cache levels. The framework is extremely lightweight, is modular, and gives high performance. IPCP only improves up to 45%, and there are still miles to go until perfect L1D performance is reached. We thank the Semiconductor Research Corporation and Intel Labs for their valuable support for our project. The source code for IPCP is available at the following link. Thank you for your time.